Now we're going to work one more example that will show you the variety, I suppose, of types of solutions that you can get. So say we had something like this, x plus y equals 3, and x plus y equals 2, negative 2. Now, when you just start looking at this, you should realize, hey, something is funky going on here, because how in the world can x plus y be equal to 3 and negative 2 at the same time? And the answer is, well, it can't. And actually, the answer to this problem is going to be that there is no solution. There's no way that x plus y can be 3 and negative 2 at the same time. Nonetheless, these problems aren't always necessarily that clear just from looking at them, so we're going to go ahead and work through it just so you can have the experience and kind of know and recognize when this comes up later what to expect. So say we're going to have a problem like this. So we're going to have 1, 0, and then we want to also try verifying 1, 1. Now neither of these is going to work. Actually, let me pick something a little different just to make it interesting. What if I go 1, 2, and negative 3, 1? Let's do that instead. That'll be more exciting, if you could say exciting. All right. So we've got 1, 2. So x is going to be equal to 1, y is going to be equal to 2. We want to test each of our individual equations. So x is 1 plus 2. Now, is 1 plus 2 equal to 3? Yes, that one works. Now let's try the second one. X is 1 plus 2. Is 1 plus 2 also equal to negative 2? No. So this one is not a solution. Not a solution. Hello, there we go. Okay, well maybe we'll get lucky with the other one. We won't because we've already established that there's not going to be an answer to this problem. So let's try plugging in x equals negative 3 and y equals 1. Again, we're going to plug it into the original problem. Alright, so for x, we've got negative 3. Is negative 3 plus 1, is that going to be equal to 3? The answer is no, it's not. So in fact, we don't even have to check the other one because in order for it to be a solution, it has to meet both requirements. So since it doesn't meet the first one, we don't even have to bother testing the second one, and we can just come up and say, you know, this is not a solution. So just for completeness sake, and actually this is a very, very important thing to do, let's go ahead and graph these and see what we get. So our first one was x plus y equals 3. So if we want to get that into y-intercept form, slope-intercept form, we're going to get y equals negative x plus 3. So that means that our slope is negative 1, and our y-intercept is positive 3, right? So if I was going to graph this thing, line, whatever, 1, 2, 3, 2, 2, 2, 2, 2, 2, that should be enough. If this is my first one, the point is at y-intercept's at 3, slope is negative 1, so down 1 over 1, down 1 over 1, down 1 over 1. So it's going to look like this. This is actually the same line we had before. Chunk. Like that. Now our second one, this will be our green problem. No, not our blue problem. Our green problem was x plus y equals negative 2, right? So if x plus y is negative 2, now again, if we solve for x, or solve for y, put it in slope-intercept form, we've got y equals negative x minus 2. So in this case, our slope is negative 1, but our y-intercept is equal to negative 2. So our intercepts are different. These are definitely different equations, but what's going on with the slope? The slopes are the same. So if the slopes are the same, what kind of lines do we have? We have parallel lines. Yep, we have parallel lines. So y-intercept of negative 2, again, the slope of down 1 over 1. And if we graph these lines, we are, in fact, going to get parallel lines. So since these lines are parallel, they don't intersect anywhere, right? They just flat out don't intersect. So since they never intersect, that means that we have no solution. Anytime lines are parallel, that means that we have no solution.